So in this video we'll be covering further rational functions. So this is kind of a second video on rational functions. I suggest you go watch the first one that we uploaded before if you don't know what rational functions are. This video will just kind of be focusing on asymptotes and how to graph rational functions without a calculator. So in this video we'll be covering vertical asymptotes, horizontal asymptotes, oblique asymptotes, and graphing rational functions. So let's get started. So first, what is a rational function? A rational function can be expressed in the form f of x over g of x, where f of x and g of x are polynomial functions, and g of x cannot be 0. And so there are three types of rational functions. The first type is when the degree of f of x is greater than the degree of g of x. And by the degree I mean the power to which the x value is raised to. So if let's say this would mean that x cubed over x, the degree of f of x, which is this top polynomial, is to 3, and in the denominator is just 1. So that's the first kind of rational function. The second kind is when f of x is less than the degree of g of x. And the third kind is when the degree of f of x is equal to the degree of g of x. So I'll write down examples for each of them. So for the first one, an example would be 2x cubed plus 3x squared plus 4x minus 8 all over 3x plus 2. Now, they do have the same degree, but the highest degree in f of x is 3 and the highest in g of x is 1. So that's when you know it's the first case. In the second case, an example can be 3x squared minus 2x plus 8 over 4x cubed minus 5x squared minus 1. So the denominator, the highest degree is 3, and the numerator, the highest degree is 2. And in the last example, you can imagine it can just be 3x plus 1 over 2x minus 5. So the degrees are the same in f of x and g of x. So a few things that we need to know before we move on into the specific asymptotes are the following. So 1 over x approaches 0 as x approaches infinity. 1 over x approaches infinity as x approaches 0 and x is greater, provided that x is greater than 0. And 0 over n equals 0, where n is not 0 and n can be any number. And x over n approaches infinity when x approaches infinity and n is any number. Any positive number, and obviously not 0. So these are the few things we need to remember before we look into asymptotes, because this will help us. Okay, so vertical asymptote. Basically what we're looking for when we're looking for vertical asymptotes is to investigate the function around the places where the denominator is 0. So we would need to know, we can basically find the vertical asymptote of any function, any rational function, by setting the denominator to 0. And I'll just show you. So on the graph on the left, we can see the graph of x over x plus 4 divided by x. And this is a rational function. And now we can see that there is no value for which this function touches the y-axis. We can see that as the y value increases or decreases, the function gets extremely close to the axis, but it will never touch. And this is what we call an asymptote. So in this case, the asymptote is x equals to 0. And this is our vertical asymptote for this function. And we can obtain this by setting the denominator to 0. So we know that the function is x plus 4 over x, and the denominator is x, so when we set it to 0, we find that the vertical asymptote is x equals to 0, which is what we can see in the graph. So that's basically it for vertical asymptote. You just need to set the denominator equal to 0. Let's look at an example. Okay, so this question says to find the vertical asymptote defined by f of x equals 3x minus 15 over x squared minus 2x minus 15. And so now we can use the factor form to, so first we need to obviously set the denominator to 0, right? So we have 3x minus 15 now if we take, we can see that this is a quadratic, and now we need to factorize it in order to get our two different roots, right? So once we factorize this, we can get x plus 3 and x minus 5. And so the denominator is 0 when x equals negative 3 and x equals positive 5. So when we graph the function, we will see something interesting. Okay, so we know we have a vertical asymptote at x equals negative 3, right? And it does say here that we would have a vertical asymptote at x equals 5, but let's see if that's true. Because if we substitute negative 3 into this function, we wouldn't get any value because it would make the denominator 0, but it wouldn't make the numerator 0, right? Because if we do 3 times negative 3, that would be negative 9 minus 15. So the top would be some negative number, and the denominator would be 0, which is undefined. But if we have 5, the numerator also becomes 0, right? Because 3 times 5 is 15, and 15 minus 15 over 0 would be 0. So that means that at x equals to 5, we don't actually have an asymptote. It's just where the denominator is 0, but in this case, the numerator is also 0. We have y equals 0 as the horizontal asymptote, and then we could obviously find the y-intercept. So that's what the function would look like. Okay, so now let's look at horizontal asymptotes. Okay, let's say we have this function, x plus 1 over x squared plus 4x plus 5. So to find horizontal asymptotes, we kind of need to do it analytically. The method is different depending on the degree of the polynomials in the numerator and the denominator. So I'll put down an image here for you guys. So the image on the right that I just pasted kind of shows you how to know what the horizontal asymptote is going to be. So if the degree of the numerator is less than the degree of the denominator, like we discussed before, the horizontal asymptote would automatically be at y equals to 0. You don't even have to think about it. The horizontal asymptote is always done analytically. If the degree of the numerator is greater than the degree of the denominator by 1, there's no horizontal asymptote, and it's an oblique asymptote or a slant asymptote, and that's what we're going to look into next. And if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the leading coefficients. And I'll explain what this means. So let's say we have f of x equals to 4x cubed plus So let's say we have this, and with the highest degree in both the polynomials is 3. So if it's the same, the horizontal asymptote would be the leading coefficients, meaning it would be 4 by 7. this would be our horizontal asymptote. It's as simple as that. And one more thing, the second point says that if the degree of the numerator is greater than the degree of the denominator by 1, there's no horizontal asymptote. So you wouldn't have a situation where the degree of the numerator is greater by the degree of the denominator by more than 1. Let's say, like, you wouldn't have x to the 5 in the numerator and x in the denominator. But keep in mind that the slant asymptote can only be when the degree of the numerator is greater by just 1. So if it's 3 and 2 or 4 and 3, then that means we have a slant asymptote. But it would be very rare for you to come across a rational function that you would have to graph where the degree of the numerator is greater by the degree of the denominator by more than 1. Okay, so oblique asymptotes are lines which the equation of such lines can be written in the form y equal mx plus c for m cannot be 0. So it's basically a linear function, and that will be our oblique asymptote. And it would look something like this. Okay, so the blue lines show us this one is the vertical asymptote, and this one is the slant or oblique asymptote. So this is kind of what it looks like on a graph. Mine is not the most accurate, but you can get the idea of what it's supposed to look like. And so these asymptotes are only seen in some rational functions with certain conditions relating to the degrees of polynomials, as we discussed before. Okay, so to find oblique asymptotes, you can do this on your calculator, and most likely you will have a calculator if you have an oblique asymptote or you need to graph a rational function. But if you do not have a calculator to graph your rational function, and it does include an oblique asymptote, what you can do is we can divide the two polynomials. So let's say we have f of x Let's say we have that. If we only consider the terms with the highest degree in the numerator and denominator, the quotient would be x squared over 2x, which is 1 over 2x, right? Because one of the powers would cancel out. So that's our first step. And now if we consider the difference between this expression and the function value, we can see that x squared plus 3x over 2x plus 2 minus 1/2 of x, this would give us x squared plus 3x minus x times x plus 1 if we factorize it over 2x plus 2, which would give us 2x over 2x plus 2. And so this is this difference is a quotient of two linear terms. We can multiply both the numerator and the denominator by 1 over x to investigate the values as x approaches infinity, which is kind of what we're looking at when we're looking at oblique asymptotes. So if we replace our x with 1 over x, we will see eventually that 2 over x approaches 0 as x approaches infinity, and so the whole quotient approaches 2 over 2 minus 0 equals 1 as x approaches infinity. And so if we subtract this value from 2x plus 2 from minus 1, we'll get 2x minus 2x plus 2 over 2x plus 2, And this would give us -2 over 2x plus 2. And so we got this expression by subtracting first 1 over 2x and then -1 from the function value. And since this difference approaches 0 as x approaches infinity, we found the equation of the oblique asymptote. So the equation of the oblique asymptote would just be y equals 1 over 2x plus 1. It is kind of a lengthy process, but again, most likely you will not be asked to graph a oblique asymptote without a calculator. Okay, so to sketch the graph of rational functions without a calculator, it's pretty simple. If we have all of our asymptotes and all of our y-intercepts, we can get a good idea of what our graph is supposed to look like. So first we need to find the intercepts, and I hope you guys know how to find the y and x intercepts. X-intercept is when y is equal to 0, and y-intercept is when x is equal to 0. And then we can find the asymptotes, which is vertical, horizontal, and or oblique. And this is kind of the only two things we need to know before we can get a good idea of what our graph is supposed to look like. So if you have the x and y intercept and your vertical and horizontal asymptote, you can already kind of sketch your rational function. And so let's look at an example. Let's say we have this rational function, and first we need to find our intercepts. So our x-intercept is when y is equal to 0. So that would be 2 by 3, 0. And our y-intercept is when x is equal to 0. So this would be 0 and -2 by 3. Those are our intercepts. And now we need to find our horizontal asymptote. So we can divide the numerator and denominator by x squared. And that's because the degree of the denominator is greater than the degree... Actually, no. Yeah, so the degree of the denominator is greater than the degree of the numerator. We can divide it by x squared. And then we would get, as x approaches infinity, f of x approaches 0. So we would get our y equals 0 will be the horizontal asymptote. And our vertical asymptote is if we just set this equal to 0, and we would get x is equal to -3.79 and x is equal to 0.79. And now if we put all this information on a graph, okay, so first let's plot our asymptotes. And so first we have x is equal to 0.79, and we have x is equal to -3.79, and then we have our y-intercept, which is -0.67. So now what we can do is test a point on each side of the asymptote. So we can test a point here, test a point here, and test a point here, and then we'll know if it's negative or positive, and if the graph is increasing or decreasing. So let's say if we take f of -4 somewhere here, we'll get 14, which is greater than 0. So over here it's positive. And if we take -3, which is here, we'll get 11 by -3, which is a negative number, so it will be here. And if we take 1, which is here, we would get also a negative number, which would be here. I'm not actually testing a point and solving them, but you guys get the idea. You just plug in into this original function and you would get the value. So now if we combine all of this in our graph, we have something. So we know that the graph always has to approach the asymptote. So over here, since it was positive, it'll be something like this. Over here it was negative, so we need to keep in mind that it needs to pass these intercepts. So it'll be something like that, and over here it was negative as well, so it would be approaching the asymptote like that. So this would be our sketch of our rational function. It's obviously not 100% accurate, but that's not what the IB would be looking for. They just want a good idea that you know where your asymptotes are and where your x-intercepts are. And that's it for this video.